Okay, so hi everyone. We are very happy to have Jennifer Coulomb from Stony University, Stony Brook University and Flatiron to give us a talk on moire tuned by superlattice potential. Hi Jennifer, please take it off, please.
Okay, great. Let me share my screen. Okay, can you see everything okay?
Yes, very good.
Yes. Okay, good. So today I'm going to talk about some new ideas that we have for engineering topological phases with a superlattice potential. So I'll explain this, but what I'm thinking about is really an externally applied potential. So you can get this in moire heterostructures, or you can also get this by engineering special gates. So I'll give some examples of this. But let me start from the beginning. So, well, first, let me start by now acknowledging my collaborators. So this was some work that started initially with Jed and Justin and Xiang, and then extended with G, our host, and Daniela at Flatiron Institute, and now also with Aaron and Syed at Stony Brook. So one motivation for this work is the long-standing challenge in our field of realizing symmetry-broken surface states on the surface of a topological insulator. So why do we want to realize these states? I think that there's a couple of different examples where we know that these states have really interesting properties. So for example, if we break time reversal symmetry on the surface of a 3D TI, we'll realize a quantum anomalous Hall state. Or if we break charge conservation symmetry, then we can realize a topological superconductor. But so far, these examples have been realized by explicit symmetry breaking. So for example, in the case of broken time reversal, we can break this explicitly by doping with chromium, which is a magnetic material. And there we can explicitly break time reversal and gap the surface Dirac cone. And this has been known to realize quantum anomalous Hall effect. And similarly, recently, there's been a lot of interest in these manganese bismuth telluride heterostructures, and that's a similar idea, alternating stacking magnetic layers and 3D TI layers. And then on the superconducting side, you can explicitly break charge conservation by putting a superconductor on top of a 3D TI, and this has been done on bismuth selenide to realize topological superconductor. But I think one of the open questions here is, can we achieve spontaneous symmetry breaking on the 3D TI surface? So this question was asked already at the inception of this field around 10 years ago. What can you get spontaneous symmetry breaking on the surface of a TI? And so I think this paper by Adi Stern and company is pretty interesting. There they looked at spontaneous symmetry breaking with ferromagnetic surface order. And so they computed this interesting phase diagram. So this phase diagram, the x-axis has these parameters. This is a function of the hexagonal warping and the Dirac cone velocity. And the y-axis is interaction strength. And so what they're showing is if you have a strong enough interaction, you will spontaneously gap the Dirac cone. So that's what these two phases are meant to show. And if you have a small interaction, you'll have a gapless surface Dirac cone. Large interaction, you'll gap the Dirac cone with ferromagnetic order on the surface. And these are different lines that are showing the critical interaction strength at different temperatures. So what they showed is that bismuth selenide and bismuth telluride, which are two of the most prominent 3D topological insulators, sit below these curves. And so we wouldn't expect them to have spontaneous symmetry breaking. And similar conclusion was reached for other types of surface order. So you could look at spin density waves, and you could also look at superconductivity. And in all of these cases, the Coulomb interaction is too small to realize spontaneous symmetry breaking. So one question then that we can ask is, well, we could consider 3D TIs that were made of more strongly correlated materials, and then maybe they would sit somewhere else in this phase diagram. But the other approach is, could we increase the density of states to make the Coulomb interaction effectively stronger? Or in other words, if we change the velocity of the Dirac cone, then we'd be moving more towards the strongly correlated side of this phase diagram. So the recent work on the new field of twistronics gives us a tuning knob that precisely does this. So there's a couple of examples that most people probably already know of. So twisted bilayer graphene, of course, is the most prominent example. Each individual layer of graphene is very dispersive, but when you put two layers together, then you can get these flat bands, which have very small bandwidth and therefore a very large effective Coulomb interaction. And another example is the twisted transition metal dichalcogenides like tungsten diselenide. And here you don't get flat bands, but you get Van Hove singularities. And these Van Hove singularities also have a very strong effective Coulomb interaction. So we might ask then, can we apply twistronics in order to enhance the density of states on the surface of a topological insulator, thereby being able to realize spontaneous symmetry breaking on the surface? So there's a few different platforms that I was thinking of in order to realize this. So one platform, so first off, we could consider different types of twisted heterostructures. So the first platform is kind of the most naive thing to do. What if we took two 3D topological insulators and arranged them with a small twist angle? So this would be kind of like twisted bilayer graphene, but a 3D generalization of it. And so I'll say a little bit more about this later, but if we do this, we can actually realize magic angle conditions, although only under certain very specific conditions that I'll describe. But this is kind of a clunky, unrealistic platform. So a more realistic platform might be to take a 3D topological insulator and put a 2D layer on top of it, thereby making a moire heterostructure just on the surface of the TI. And so the effect of this 2D layer would be to impose a superlattice potential on the 3D TI surface, as long as these layers are very closely lattice matched. So I'm basically thinking of making a moire pattern on the surface of the 3D TI. But there's also a more direct way to do this, which is instead of making a moire heterostructure, what if we just directly pattern a potential? So in this right-hand picture, what I'm trying to show is we have our 3D topological insulator. On the surface, we have some 2D dielectric material, and we punch holes in a regular way in that dielectric material. Then if we put a gate on top, the field that the topological insulator sees from the gate will be spatially modulated according to the pattern in this dielectric material. So these two different setups on the left and the right here are actually two different ways of realizing effectively the same Hamiltonian, which would be the Hamiltonian of a 3D topological insulator plus some what I call a superlattice potential, which is just some spatially modulated potential, spatially modulated in both directions. So this is the Hamiltonian that we want to study for a little bit, and then I'll actually come back to this system. So the main, what are the main features of this? So let me just try to give a little bit of intuition of what we would expect. So this is our surface Dirac cone, and the superlattice potential will have some wave vector. And so what happens is that the superlattice potential, the effect of it is to couple different K points on different sides of the Dirac cone that are separated by this wave vector, basically folding the Brillouin zone. And so that makes a Dirac cone like this be folded into some more complex configuration, which is shown over here. And what you can see from this configuration is that actually you still can't have any band gaps because this is the surface of a topological insulator, and the anomalous surface state cannot be gapped because so far we haven't said anything about Coulomb interaction. So time reversal symmetry protects lots of crossings, and we call these crossings satellite Dirac cones. So this is our original Dirac cone, but at other energies, there'll be other places where the bands touch. So we kind of label these by X1, M1, gamma 1. All these are called different satellite Dirac cones, and they're protected by time reversal symmetry. And if you look at the density of states on the surface, you can detect these different satellite Dirac cones by these different dips in the density of states. So the main feature that we get from a superlattice potential on the surface of a TI is gapless satellite Dirac cones. The second feature is you renormalize the Dirac cone velocity. So I'll say more about that, but basically what happens is that as you're opening gaps on kind of the sides of the new Brillouin zone from band folding, you push bands down. And so that changes the velocity of your original Dirac cone. And then finally, the other point is that you get these Van Hove singularities. So, the satellite Dirac cones I've already mentioned, and now I'm going to talk in a bit more detail about these renormalized Dirac cone velocity and the effect of Van Hove singularities. So how can we get a handle on this, on how the Dirac cone velocity changes from the superlattice potential? Well, the first thing that we did was kind of do a generalization of Bistritzer-McDonald model, which is just to take the leading order in perturbation theory. So our Hamiltonian is the k dot sigma on the surface of the TI, and then we impose this superlattice potential, which has some wave vectors q. And if you do the leading order in perturbation theory to find the effect of the superlattice potential, what you'll see is that it changes the Dirac cone velocity in the following way, which I've wrote down here. So the velocity gets changed to v star, which is the original velocity multiplied by this factor of 1/1 plus alpha. And so this parameter alpha, I've written it here in some formal way, but let me just say the numerator of alpha is the strength of the superlattice potential, and the denominator is the wave vector. So we can understand this by comparison to twisted bilayer graphene. If we increase the strength of the superlattice potential, which in TBG would be like applying pressure and pushing layers of graphene closer together, then we increase this parameter alpha, which means we decrease the surface Dirac cone velocity. So that's like pushing you closer to the magic angle in twisted bilayer graphene. In the other direction, if we increase the wave vector, which is like making a smaller supercell or smaller superlattice or smaller moire unit cell, if we increase Q, then we decrease alpha, and then that pushes the velocity in the other direction. So there's some similarities here to twisted bilayer graphene, but there's a huge difference, which is that the new velocity goes like 1/1 plus alpha. In other words, you never realize a magic angle. So in twisted bilayer graphene, you have two Dirac cones, and so they have a more complicated interference pattern. That means at some specific angle, the velocity can precisely vanish. What we realize here by applying a superlattice potential to the surface of a TI is that we can change the Dirac cone velocity, but it changes monotonically and it never reaches zero. So that's the big difference between this system and the system with two Dirac cones. So this perturbation theory is kind of a little bit too simple. It gives us some handle of what's going on, but in order to actually to check it, what we then did was turn to some really nice numerical simulations. So on this slide, what I'm showing is we take a model of the Bernoulli-Hughes-Zhang model of a 3D TI on a cubic lattice, and then we add our superlattice potential to the surface. And so we can then track what happens to the velocity of the Dirac cone as a function of the superlattice potential strength. So this plot is showing Dirac cone velocity as a function of superlattice potential strength. And we should be looking at these blue curves up here. So let me say the blue line is the perturbation theory that I just described, but going out to much higher orders in perturbation theory. It's actually 5th order in perturbation theory. The dots are numerical simulations. So what you can see is that the perturbation theory and the numerics agree reasonably well. We need to go to higher orders to get them to agree better. But the other interesting thing that you see by following these blue dots is that there's actually a minimum here. So for some reason, the Dirac cone velocity, it doesn't reach zero and it doesn't decrease monotonically, but it reaches some minimum value. And that minimum value is around 1/3 of its original value. So I drew in this dashed line just to see, so that we could compare. The new Dirac cone velocity at its minimum is roughly 1/3 of the original velocity. So the takeaway message here is that we can use this superlattice potential to severely modify the original Dirac cone velocity, but there is no magic angle, and it doesn't seem like we can even get arbitrarily close to zero. Question?
Yes. So one difference with graphene is also that there the superlattice potential, if you wish, has some structure in the spinor space. There it is the sublattice space. Here it will be spin space. So have you thought, just for a second, I mean, it might not be realistic that you have a modulated magnetic field rather than scalar potential, because then there will be some structure to this quasi-periodic potential in the spinor space, and maybe that is related to magic ultimately.
Yeah. Okay, good. So I think that there actually is some other paper that came out after our work, which is precisely what you just said, looking at like a magnetic potential, which is spatially modulated. So the difference there is that you're going to explicitly break time reversal. So then you're going to allow a gap to open on the surface explicitly. That's fine. So you can do that. And you can, I think then you can actually get probably Chern bands on your surface. That's kind of the general thing that happens when you break time reversal symmetry. But the other thing which I mention later is that it's precisely what you just said. We could also consider, just like we considered 2 Dirac cones and twisted bilayer graphene, we could consider the first setup I showed, which is taking 2 3D TIs and making a twisted heterostructure. And in that case, the modulation will be in spin space instead of sublattice space. And that has consequences for, well, basically that has consequences for the different type of interlayer hopping that you would need to realize a magic angle. So maybe I can just come back to that like in a little bit.
Thank you.
Yeah, thanks for the question. Please feel free, anyone, to ask questions. Okay, good. So the point here is that we can change the Dirac cone velocity with the superlattice potential, and we can actually change it quite significantly. We can also, instead of changing the strength of the potential, we can also change the wave vector, this wave vector Q. And so again, the solid lines are showing our perturbation theory, and these dots are showing numerical simulations at different system sizes corresponding to different size superlattice. And so the numerics and perturbation theory agree pretty well. And you can again see that the velocity is dipping down to a fraction of its original value. And I think that these dots would keep going down, except that we couldn't get to large enough system sizes. So then the question, I think one of the natural questions is, regarding material realization, can we make a moiré heterostructure on the surface of a 3D TI? So the challenge is that we need to find some 2D material, which is lattice matched to the TI surface and ideally insulating so that the only effect is to create a potential. And we don't have a material like this in mind. The lattice matching is a pretty strong constraint. If you're not well enough lattice matched, then what happens is that you end up with too large of a wave vector, which mixes the bulk and surface states. So we never found a promising material combination. And so that led us to the second route that I was describing, which was, well, what if instead of a moiré heterostructure, we make this externally imposed superlattice potential? So to model that situation, we wanted to do something which was more realistic. And so we made a vanirization of a slab of bismuth selenide. So let me explain what this band structure is showing. So the gray lines are our ab initio calculations. So this is it's a slab of 5 quintuple layers of bismuth selenide. So the gray lines are showing the ab initio band structure, and then the red lines are showing some vanirized type binding model. And at the higher energies, they differ, but at the lower energies near the Dirac cone, which is where all the surface physics is, then they agree reasonably well. So this is a zoom in showing the surface Dirac cone from the ab initio calculation in gray, and the surface Dirac cone from our vanirized type binding model in red. And for the very low energy physics, these things agree reasonably well. We need to make this vanirization because we want to impose our superlattice potential, which is naturally in real space, not in momentum space. So with this Vannierized model, then we can actually explicitly apply a superlattice potential on the surface. So that's exactly what we do. We chose to apply a triangular lattice superlattice potential with a period of 12 nanometers. And we chose that 12 nanometers just because it's the same scale as twisted bilayer graphene, which seems to be a really nice length scale. So that seemed like a good place to start. And I should say these calculations were done by Shang, who's now a postdoc at MIT. So what do we find with this? So this is the same type of plot. I'm plotting Dirac cone velocity as a function of the superlattice potential. And so this red curve is showing the Dirac cone velocity of the original Dirac cone. The others are showing the satellite cones that I was talking about earlier. And so you can see kind of the same effect that you saw in our toy model, the BHC model, which is that the Dirac cone velocity reaches a minimum and then comes back up again. And that minimum seems to be roughly 1/3 or 1/4 of the original Dirac cone velocity. So I think that this is actually, I think it's actually pretty neat, because in these two systems, one was our toy model and one is this more realistic model, starting from an ab initio calculation, we kind of see the same trend. The Dirac cone velocity decreases, it reaches a minimum, it comes back up, and its minimum value is roughly 1/3 of its original value. Now, how realistic are these parameters? I want to say that actually this idea, making a spatially modulated superlattice potential, was carried out in Corey Dean's group a few years ago on graphene. And so there they were able to realize the smallest superlattice they realized was around 35 nanometers, and the potential went up to around 50 MeV. So in this model that we just did, the superlattice is 12 nanometers, and to reach this absolute minimum, we're going up to 200 MeV. So it's slightly outside of their parameters, but it's within the same order of magnitude. And probably in general, a larger superlattice makes for flatter bands. So actually, if we increased our superlattice potential period to be bigger on the order of what they realized in their previous experiment, it might not take as large of a potential in order to realize this minimum point. So I think that these values are within the reach of experimental parameters. And so then the next question is, well, is this Dirac cone renormalization actually significant? So if we go back to this previous plot that I showed from Adi Stern's work, then what we see is that, remember this, the x-axis is a function of two things. The lambda is hexagonal warping and the V0 is the Dirac cone velocity. What we've shown is that the superlattice potential can change the Dirac cone velocity by roughly down to 1/3 of its value. So I drew these arrows in which show where bismuth selenide and bismuth telluride would be if we shifted the Dirac cone velocity by a factor of 3. And you can see, especially for bismuth selenide, it pushes it right into the range of these critical curves that they computed. So if we could achieve this level of Dirac cone, of changing the Dirac cone velocity, then it's possible that we would be able to realize the regime of spontaneous magnetic order on the surface of the TI. So I think that's a pretty significant development. So so I said that the superlattice potential can change the Dirac cone velocity. The other major effect of this potential is to introduce Van Hove singularities. And so we can see it from this band structure. So these dashed lines are our original Dirac cone velocity, and then these solid lines are the new band structure just after the band folding from the superlattice potential. And so you can actually see by, say, comparing the original band structure to the new band structure, you can see the change in velocity that I was talking about, but you can also see that higher up in energy, these are the Van Hove singularities. And so it was pointed out in this nice work from Liang Fu's group that actually these Van Hove singularities are occurring near the K point, and there's 3 of them. There's 3 of them which are near K, and there's some critical value of the superlattice potential where they'll coalesce into one higher order Van Hove singularity exactly at the K and K prime points. Is there another question in the chat, by the way? I can't see the chat while I'm screen sharing, so speak up.
Yes, I can
Yeah.
read the question. It's from the Martin. So is there a physical diagnostics experiment that demonstrates this?
That demonstrates the change in Dirac cone velocity. Yeah, so good.
That's what I wanted.
Yeah, so I think that there's two things to do. One would be in transport, you could measure the surface density of states. So you could see these, so this is the density of states. You could actually see these different dips. Yeah, so this dashed line is actually density of states without any potential. And then these blue lines are showing the DOS with the superlattice potential. And so I think you could be able to measure these dips by peaks in resistivity. That's the easiest way that you could measure this. And that would actually be a way to show that I think that's the simplest way to show that your superlattice potential is doing anything at all. More optimistically, if you could actually reach the regime, this regime that I was showing on the previous slide, if you actually did cross the critical line into the gapped phase, well, then you'd have spontaneous symmetry breaking on the surface and you can measure the anomalous Hall effect. But to figure out whether you're en route to that regime, I think it'd be better to try to measure the DOS in transport. Okay, good. So I hope that answers the question. Good. So the other thing that I want to say is, right, we have this change to Dirac cone velocity, and we also have these Van Hove singularities. And the important thing to note is that we're talking about two different energies here, because the Dirac cone velocity is something that we can measure near zero, near the original Dirac cone energy. And the Van Hove singularities are happening at 2/3 filling of the new superlattice unit cell. So this would be, right, it's at the K point, and you can kind of see it's a lot higher in energy than the original charge neutrality point. So these are two different types of places where the density of states is changing a lot. And so we wanted to figure out, well, at these Van Hove singularities, what type of instability can you realize? So now you can kind of clearly see that there's actually 3 Van Hove singularities that are nearby the K and K prime points. And so what we then wanted to figure out was, well, the K and K prime points are connected by well, they're separated in momentum space. And so these instabilities are going to drive some kind of density wave. And it turns out that they will drive a spin density wave because of the spin momentum locking on the TI surface. So in other words, we know that as you go around the surface of the TI at the K point, spin is pointing one way, at the K prime point, it's pointing another way, and it'll keep on rotating as we go around the Dirac cone. And so if there's any kind of instability with a wave vector that is connecting the K and K prime points, then that's going to connect states which have different spin. And so this is going to drive a spin density wave. And so we then study this magnetic instability. Are there any other questions?
Yes, you can unmute yourself. Yeah, there's a question. How can I calculate density of states in magnetic TI heterostructure with applied magnetic field?
Yeah, well, I guess it depends on what setup you're thinking of. If you're thinking of so maybe I should just say things that are specific to our work. We're just computing the density of states. I guess, in the usual way. Which is to take the block wave functions at each energy and see how many states there are. If you apply a magnetic field, you can apply it in 2 different ways. You can consider the Zeeman term, or you can consider quantization. And the Zeeman term will just open a gap at the Fermi level. I don't know if that answers the question.
Yeah, I think this answers the question. Yeah.
Yeah, okay. Great. So what I was saying is that we have Van Hove singularities near the K and K prime points, and there's nesting vectors that connect them. And these nesting vectors are drawn over here as delta 1, delta 2, delta 3. So for example, if you look at this delta 1, That's this vector connecting the K and K prime points. And similarly, delta 2 and delta 3 are these other vectors. So there's those three possible nesting vectors. And since the K and K prime points are different points in the Brillouin zone, then there's going to be this sort of density wave is going to make a larger unit cell. And so we've drawn it here. The black hexagon is the original Brillouin zone, and the blue hexagon is going to be the new Brillouin zone that results from having this spin density wave order. So the spin density wave creates a larger lattice, which means it creates a smaller unit cell. So we can then study this model. The model will be our TI surface. That's just this K dot sigma. We wrote it here as K cross sigma. Those are the same. Our superlattice potential, which is this term here. And then we can consider what happens now if we have just some on-site Coulomb interaction, which we've written as H int here. We can then use mean field theory to look at the magnetic order parameter that minimizes the free energy. And I just want to emphasize that this magnetic order parameter is actually in kind of a 9-dimensional space, because it itself is a vector, so it has x, y, z components. But in addition, we have these 3 different nesting vectors, delta 1, delta 2, delta 3, that connect the K and K prime points. So in total, there's 9 different parameters that we can optimize in order to minimize the total energy at the mean field level of this Hamiltonian. So that's the thing that we want to do. And when we carry out this mean field procedure, so this was done by Daniela Guerci's postdoc at Flatiron Institute and also by G. The resulting spin density wave that we find is actually much more interesting than we were even thinking about. It realizes what I call a meron lattice. So let me first remind you what a meron is. So remember a skyrmion. A skyrmion points up in the center and has a spin that would point downwards at the boundaries of the system. So a meron, which we've drawn here, is actually half of this. It's a spin that points up in the center and points in plane at the boundaries. And so this is actually a rather unusual spin configuration. I think it's unusual because if you're going to, usually we think about like compactifying space. And because for the meron, the boundary condition is in plane, all over the boundary, it's pointing in different directions. And so you can't really compactify the space the way that you can for a skyrmion. But if we have a 2D plane and we have multiple of these merons, then we have no such problem. We're not really trying to make a unified boundary condition. So this is precisely the sort of spin order that comes out of our mean field calculation. So we've drawn it here. Let me say a little bit about what it means. So all these different arrows are showing this mean field magnetic order, and the length of the arrow is showing the magnitude of the XY component of spin, and the color is showing its Z component. So if we look, for example, in this hexagon, we see at the center, the spin is, this red color is meaning that the spin is pointing, say, out of the page. And if we look here at the neighboring hexagon, it's pointing into the page. So these are kind of merons and anti-merons. And if we look along the boundaries of all of these hexagons, the spin is pointing perfect. It has no Z component. So it's perfectly in plane, and it's rotating around as you rotate around the hexagon. So this is precisely a meron realized in this supercell. So one of these honeycombs is our original lattice, or the lattice which is set by the superlattice potential, and the magnetic order makes a larger superlattice than that, which consists of 3 of these different honeycombs, which is what this kind of bright blue hexagon is showing. And within each of these bright blue unit cells, we have one of these merons, one of these anti-merons, and then a hexagon that doesn't really have that much spin order happening in it. And for each one of these hexagons, we actually computed this Pontryagin number, which is the number, if you had a skyrmion, this thing would be 1, but for a meron, it's 1/2. So we computed this, and in each one of these triangles, it integrates precisely to 1/2. So these things are exactly merons, which of course they had to be because the spin on the boundaries is perfectly in plane. So this is a really unusual spin configuration, which is stabilized by the combination of spin orbit coupling and the superlattice potential. Now, in the beginning, I kind of motivated this by saying that we might want to realize spontaneous symmetry breaking on the surface of the TI so we could realize quantum anomalous Hall, but that doesn't happen here because actually this meron order, it preserves C2T symmetry. So let me say what that means. So that's the product of time reversal and a twofold rotation. So if you look at this spin configuration, if you rotate by 180 degrees, you'll swap the merons and antimerons. And if you then impose time reversal, which flips all the spins, then you'll get back to your original configuration. So the combination of pi rotation and time reversal symmetry leaves this magnetic structure invariant. But that C2T symmetry also protects Dirac cones, so it prevents a gap from opening on the surface of the TI. So we have a gapless magnetic order. And you might wonder, well, how does that save any energy from the Van Hove singularity? But it actually splits the Van Hove singularity into two different peaks. So previously there was just one peak, now it's split into two. So that's where the energy saving comes from. And you can see, so this is our, this is the mean field band structure after imposing magnetic order. And this is the resulting Fermi surface. So you can see that the surface is gapless, and because the magnetic order preserves this symmetry. And also because of the symmetry, you won't realize any anomalous Hall effect because the different magnetic, the total configuration will be vanishing. So this is a way to realize spontaneous symmetry breaking on the TI surface, but there's not going to be a quantized Hall effect that comes along with it. One way that you could get a Hall effect is by breaking this C2T symmetry. And in fact, actually the surface of the surface of bismuth selenide and bismuth telluride, actually this is only approximate symmetry. It's not exact because those surfaces don't have a pi rotation. They have threefold symmetry, but not sixfold. So for those particular materials which actually don't have this symmetry, then there will be, or I shouldn't say will be, it's symmetry allowed. There could be an anomalous Hall term. And it remains to compute what the magnitude of that term would be. So one question then is, can we actually realize these phases? Is there, Juven, do you have a question?
Yes, Jennifer, a very nice result. Can I ask something earlier? So the TI has U1 and time reversal symmetry, at least in the bulk, right? Mm-hmm. And however, you say that even though it's magnetic order, it breaks T but not breaks C2T, right?
Yes.
And how about U1? Just remind me.
Oh, yeah. So U1, the U1 is preserved by this order because it's magnetic order, not superconducting order. So what we could do, and actually something that we're thinking about now, we only looked in the magnetic channels. And so we can compare magnetic and superconducting channels. There's definitely going to be some kind of superconducting instability. It just depends on how the superconducting instability compares to the magnetic instability in which of those two things is dominant. So that definitely will happen. And it's just a question of energetics, which is dominant.
Okay, that's very, very nice. Let me remind me the relation between C2 and the U1 and T in the group structure. So U1 and T are semi-Dirac product, right? And they share the Fermi parity. But C2 here, how does C2 and T commute?
So C2 and T, so C2 is just the spatial rotation. So the spatial symmetries all commute with time reversal symmetry. And I think that those things would also all commute with the U1 symmetry because I don't see why they wouldn't.
Okay, okay, thanks.
Yeah.
So the full symmetry for this magnetic order preserved, is that correct to say U1 semi-Dirac C2T? Is that still this structure? U1 semi-direct C2T. I'm just trying to figure out on my head, say, what are the possible survey state. The one you find out is very interesting. I was just trying to figure out what are the possible. Is the symmetry group right now is U1 semi-direct C2T.
Yeah. So that's definitely, I mean, there's other symmetries as well. So there's also threefold rotation, and there's also one of the mirror symmetries is preserved. So there's a few different mirror symmetries, which are like cutting either this way or cutting through the middle of the hexagons this way. And so, right. And so I think that this is the mirror symmetry that's preserved. So there's a mirror, there's a C3, there's C2T, and then there's U1 symmetry. Those are all, I think those are all the symmetries of this model once we realize this magnetic order.
Thanks. And just remind me last time, the gapless order here, the gapless is due to which excitation?
Yeah. So I think the gapless is due to C2T because C2T basically gives you a winding number around a Dirac cone.
Okay, and gapless is still due to the Dirac cone, not due to the time reversal breaking. It's due to Dirac.
Yes, exactly. So you started out being gapless because you had a Dirac cone, and the time reversal breaking kind of folds the Brillouin zone, opens up gap. So basically, before you had the magnetic order, actually at K and K prime, all of these, the red and the blue and the green bands were all sitting in one place. The magnetic order folds the Brillouin zone again. So then you open these little gaps here and they kind of, you split from one band to being three different bands. So the fact that you don't completely gap the band structure when doing this, that's the C2T symmetry. If that, does that make sense?
Yeah, thanks very much. Thank you.
Yeah.
Thank you.
Yeah, and I guess in general, I should say, if you really wanted to consider all the possible pairing channels, you should restore C2 and T symmetry separately, and then kind of go down from there. Like this is one channel which breaks C2T, but you could also consider other types of pairing channels. Yeah, and we considered all the magnetic channels, and it turns out that this is the one that minimizes energy. And we looked over, this is kind of always the one that minimizes energy within magnetic channels, but in principle, you can have other different orders that would like break T, but preserve C2. You know, there's other different possibilities. This is just the one that we found. Okay, good. So the only other point that I wanted to make is that what we would really like to know is what is the critical temperature of this phase. And so in order to answer that question, we had to pick some value. We had to pick some value for the Hubbard U. That was our on-site interaction term. And then we can see how big this phase, the region of this phase is as a function of, these are the parameters of the model. So W is the superlattice potential strength, VF is the Dirac cone velocity, and L is the period of the superlattice. So we put in some kind of what we thought were reasonable parameters, which means that this ratio will be around 1.5. So that's kind of sitting right here. So that brings us to basically the peak of the spin density wave phase. And for this value of U, the critical temperature is on the order of a few Kelvin. So this is something that can be reached in an experiment. But the major caveat here is that we kind of pulled U out of thin air because, well, we don't really know what the dielectric constant would be. And so I think that's actually a big question if we're thinking about actually what would the real numbers be in the real material. We need to know the value of the dielectric constant. And actually, as far as I can tell, this is not published in the literature for the surface of a TI, which can be different than its bulk value. Okay, so let me actually, there's just a couple of things I want to say in the kind of last 10 minutes and save some time for questions. So let me just say, this is coming back to the question that was asked earlier a little bit. Instead of imposing the superlattice potential, can we come back to this kind of weird setup that I proposed, which is, can we make a moiré interface between two 3D TIs? So we take two 3D materials and twist them and look at their interface. There'll be one Dirac cone from each layer, kind of like twisted bilayer graphene, and then these Dirac cones can gap. And the question is, can you realize flat bands in between here? And so why am I thinking about this? Well, all of the previous work that I just said was looking at the different effects that we can see if we impose a superlattice potential on the 3D TI in order to manipulate its Dirac cone velocity. But now I'm going to ask, can we manipulate the Dirac cone velocity in a different way by making this twisted heterostructure? And the problem is that the Dirac cones in a TI, unlike graphene, are at the center of the Brillouin zone. So if we twist them and we assume a perfect isotropic Dirac cone, then they're not offset in momentum space. So we need to consider a fictitious situation where the Dirac cone is at the boundary of the Brillouin zone. So my student Aaron studied this problem, and he finds that we looked at the square lattice. If you do consider your Dirac cones at the boundary of the Brillouin zone, then you can get a magic angle. But so now this is connecting to the question that Pavel was asking earlier. You only get that magic angle if your interlayer hopping is flipping spin. So you can kind of understand this because if you offset these two Dirac cones and you consider the spin momentum locking, you'll see that where they cross, their spin is pointed in opposite directions. But we can also understand this by analogy to twisted bilayer graphene, because in twisted bilayer graphene, the Dirac cone is made of sublattice and not spin. And what we know from studying the chiral limit of twisted bilayer graphene is that you can realize flat bands if you're you can only realize flat bands if your interlayer hopping flips sublattice. If you have only the same sublattice hopping, then you can't realize flat bands. So this was explicitly pointed out in this work. So now, since our Dirac cones are made of spin, the same logic holds, and we can only realize flat bands if we have interlayer hopping that flips spin. Of course, the difference is that in graphene, having interlayer hopping that flips sublattice is completely allowed. There's nothing that protects sublattice at all. So there's nothing weird at all about having an A to B interlayer hopping term. But in this model, there is nothing that prevents a spin flipping hopping term, as long as you choose another spin to preserve time reversal. But it's kind of a weird term. It's just not something that's very natural, and we wouldn't expect this term to be large, although it's allowed. So in general, on physical grounds, we wouldn't expect to see flat bands. We did actually look at what the Dirac cone would look like. So Aaron plotted all these different surface band structures. This is just the original 2 Dirac cones, one from each layer, folding the band structure. And as you start turning up the interlayer hopping with the spin flipping term, you can realize this kind of magic angle type case where bands start getting super flat in here. But actually, it still is different than twisted bilayer graphene because these flat bands never detach from the other bands. So they're never completely flat, even though the velocity can get very small. So this red line is plotting the velocity that he extracts from these plots. And you can see that this thing gets very close to 0. This is from the solid line is from these band structures above, and the dashed line is from perturbation theory. So the takeaway message is that you need a spin flipping term to realize magic angles in this 3D TI interface, which was already a somewhat fictitious model because we pretended that the Dirac cones are at the corner of the Brillouin zone, even though in all materials we know they're not. So we don't consider this to be a particularly promising route for the materials we know right now in order to manipulate the Dirac cone velocity. And there's some other options that we considered, but the conclusion is the same. So so this is kind of a summary of what I've said so far, but I just wanted to say something else in the last 5 minutes. So what we've said so far is these different routes to manipulating the Dirac cone on the surface of a TI. We can change the velocity basically up to a factor of 3, which is a lot. And we can also induce Van Hove singularities, which give us this meron lattice instability. In the last, say, 5 minutes or less, I just want to summarize a different platform that we've been working on recently this summer that I think is really interesting. So let me just say quickly 5 minutes about this new topic, which is what if instead of applying our superlattice potential to the TI surface, we apply it to other 2D materials? And specifically, we're thinking of bilayer graphene. So we're thinking, here's the setup. It's bilayer graphene, not twisted, just regular Bernal-stacked. And there's a top gate, which is spatially constant, but then on the bottom, we have a superlattice gate, which imposes a superlattice potential. And there's been a lot of literature on superlattice potentials in graphene, but there has been absolutely no literature on looking for topological flat bands with this superlattice potential. And so that's the thing that we're looking for in our work. And so the intuition, let me give some intuition of what will happen. So bilayer graphene, Bernal-stacked bilayer graphene realizes these quadratically dispersing bands. If you apply a displacement field, which is a perpendicular electric field, you can open a gap at the Dirac cones, and you also kind of flatten the bands a little bit. And then finally, if you apply the superlattice potential, I've just drawn it sketchy here, you open up gaps at the corners of the Brillouin zone. So now you get some band corners that are coming from the new superlattice, the superlattice that you've imposed. So that creates additional band folding and opens additional gaps. And so from this, you can create very flat bands. Since the displacement field already created a valley Chern number, these bands will kind of inherit some of that topology. And so what we find from our numerical calculations, this is done by Sayed Gorashi, a postdoc in my group at Stony Brook, he finds exactly that. So he finds that for a superlattice potential of a relatively modest size and pretty small fields, we can realize very flat bands, and these bands can have a Chern number, and this is rather generic. So tuning these parameters can make the bandwidth as flat as we've shown. This is a very small bandwidth, but the fact that you realize a band with a Chern number near the Fermi level is actually, that doesn't require any fine tuning at all. So we think that this is a generic route to realizing topological flat bands. We also find that for certain values of these parameters, you can realize bands that have higher Chern numbers. These are not as flat, and they're kind of mixed in with the other parts of the spectrum. So it's not clear that these will be a useful place to look for the sorts of correlated phases that we'd be interested in finding in higher Chern bands. But I think that these Chern 1 bands, which are isolated, flat, near the Fermi level, I think this is a pretty exciting development. And there's another regime as we turn up fields where we can realize trivial flat bands that are spanning a very wide range of energy. And so let me just make one final comment, which is it seems like the triangular lattice is better than the square lattice for realizing these phases. I don't exactly know why they have different symmetry properties. The square lattice has an extra particle hole symmetry just from its geometry, but it's not clear to me why that would influence the topology. So it seems like triangular lattice is the way to go. So I think that these superlattice potentials give an interesting new platform, which should be compared to twisted bilayer graphene. Twisted bilayer graphene has 2 layers of graphene, and they create a large superlattice. In bilayer graphene with our superlattice potential, we have those same ingredients. The difference is that in the externally imposed potential case, the superlattice potential doesn't modulate the interlayer coupling, while on twisted bilayer graphene it does. Having this superlattice potential gives a lot of tunability. You can tune the geometry, you can tune the length scale, you have a lot more control. In twisted bilayer graphene, you have less control, but it seems to naturally hit a very sweet spot. And so we might hope that in the future, as we get better control over the superlattice potentials and can make them smaller, that this platform, this new platform, could compare to twisted bilayer graphene, which is a lot to ask, because twisted bilayer graphene has kind of been a pretty magical spot in the recent past to look for correlated topological phases. Okay, so in conclusion, I think that we're motivated by moiré physics to think about other ways to make superlattices, and it turns out that externally imposed superlattices give us a really interesting tuning knob to apply to different types of topological states. And for us, what's motivating this work is to try to get closer to realizing basically spontaneously broken symmetry. So on the TI surface, we want to realize quantum anomalous Hall or topological superconductivity. In our 2D materials, what we're thinking of is what's the best platform to realize a flat Chern band and a fractional Chern insulator. And we're going to explore this until we can figure out what the most promising place is. So with that, I will end here, and I'd be happy to take any other questions.
Can I ask a question?
Yeah.
Hi, Jen. This is Yangzi. Thank you for a very interesting talk. So my question is actually about the last part. I'm wondering what's the superlattice constant for your potential?
Yeah.
And also
exactly.
I'm curious if you consider putting a for example, tungsten dicyanide on top of bilayer graphene, what will you
Yeah.
expect? Will you expect
Yeah.
similar thing?
Good question. So the first question is easy. We were always looking at 50 nanometers, and we chose 50 nanometers because precisely because it can be achieved pretty easily, relatively speaking, in the experiment. But we looked at many different length scales, and the physics is basically the same. It kind of just depends on the ratio of these parameters. So there's no magic length scale to be realized here. The right length scale is going to be larger, means smaller Brillouin zones, so flatter bands. But experimentally, if your superlattice is too big, your system will be too disordered, and you won't be able to maintain coherence over many unit cells. So there's some experimental fine tuning, but theoretically, any length scale will work. Okay. The second question.
Sorry, Jen. What is V0 here? Is
yes. Yeah, sorry, I went quickly. So V0 is there's a spatially constant displacement field, and there's a superlattice, because we have two different gates.
Yes. So what's the
V0 is the spatially constant field, and this is the spatially varying field.
I see. So you are actually looking at I would say, yeah, so it's not like generate a huge gap, unlike those superconducting Bernal bilayer. Okay, good. Okay.
Yeah. It depends on what this length scale is also, but right, the point is that kind of just perturbatively we can realize these bands. We kind of just need to gap them, and the Chern number is waiting for us. You just need to open gaps to make the flat band.
So if I change V0, if I increase V0, should I imagine I should make L smaller?
Yeah, I think that's right.
Thank you.
Yeah, and then the second question that you asked about tungsten diselenide on this system. So it would be very interesting. I don't know how the lattice constant of okay, so there's two different things. Tungsten diselenide can impose you can get proximity spin orbit coupling on graphene. So it would be interesting to consider the effect of that. That's item one. And the second possibility is that could you actually create the potential from tungsten diselenide? Would it create a superlattice potential on graphene? And that would probably depend on their lattice constants and how they compared. So I don't know the answer to that, but I suspect you could get proximity induced spin orbit coupling, and that might be an interesting direction.
Yeah, thank you, Jen. So maybe we should discuss offline, and I will email later.
Yeah, I'd be happy to.
Okay, thank you.
Hi, Jennifer. I have a simple question. So, in the twisted topological insulator part, so what if the two Dirac cone has opposite helicity? Do you still need the interior spin?
Yeah, good question. This is great. So Aaron actually did consider this case. So it seems like my little picture is a little bit too simple. Right, so Aaron did consider this case, and whether the Dirac cones have, okay, good. If they have opposite helicity, then you don't need spin flipping to open a gap. That's true. So there's kind of if they have the same helicity, you need a spin flipping term. If they have opposite helicity, you don't. What we think is that if you had two of the same material, they would probably have the same helicity, although I'm not sure what requires that, but I would think that they would be the same. So but you could imagine you had two different materials with opposite helicity. So that would be kind of that would be the most promising route to this, but I don't know what those materials would be. Right. Yeah, so I'll just leave it at that. Yeah.
Yeah, thank you. This answers my question. Yeah. Do I have further questions? So if not, let's thank you, Jennifer, again for the very wonderful talk.
Thanks, G. Thanks for having me, and thanks everyone for the questions.
Okay, thank you a lot. See everyone next week. Bye.